Okay, so we're gonna get into 7.1-4. So here we have a constant force P here, yes, and you're gonna apply that force to a block, and it's gonna go a distance d. We have to rank 1, 2, 3, 4, 5, 6 situations, and we're gonna rank it in terms of work done by that force P, and we will rank it from the greatest to the least. Okay, so let's see. Alright, so when we take a look at it here, we can see that A, when you look at it, see this force and the motion is going that way. Motion being identified by velocity, motion aspect, which is velocity. So the force and the velocity, they are in the same direction, so therefore you're gonna have your work, okay, done about that distance with the force, okay. And then when you compare this with other stuff, they're in a different, a different direction. The force is perpendicular here at an angle here, the force is opposite, and the force is on a slope, okay. So therefore these will be less than that because they're not in the same direction. But E has the same direction, going force P and your motion direction is going the same direction and resulting in the same distance amount, see. So they didn't say, even don't get into 2 times velocity. It means that it just fast, but it took the same distance from here to there, with the same force. And your work depends on force, and distance has nothing to do with the velocity, by the way, So don't go into confusion with this 2v. Don't assume that the work got to be 2 times because I'm going fast. No, you can go fast. You can even go 4 times. But as long as you're making the same distance with the same force, you will produce the same work, okay? So therefore, how fast you do the work doesn't matter. It's only the amount of the work, okay? So these little things that that I'm trying to teach you, yes, to respect the professor, because you're gonna miss it. At least about 80% of the student will miss that. They might understand in a lecture, when they read it, but then when they actually do the exam, they forget about it entirely and then go into confusion and choose like this is like greater than that, of course. But no, they're the same. So therefore, they only have the greatest amount of work, A and E. Then we're gonna take a look at the rest of the problem. C is gonna go the least. Okay, so therefore I'm gonna just put it in because it's opposite. See, the direction of the force and direction of the motion, they are opposite. So therefore the work done will be the least. Even you can see this negative sign is showing you that you will have to multiply with a negative, meaning I'm going in a different direction. So therefore the amount of work done is going to be different. You won't make it that distance, because of this push is going that way. So now we come to the 3, yes. And when you look at it, this is force at an angle, and this is directly, see this how it is completely 90 degree, yes, to the normal. So when you have a 90 degree to the normal, you have no work. It is indicated by that. So so no work is a little better than negative work. So therefore, yes, you're gonna see like this is no work. This means like you're working to the opposite direction. Okay, so therefore this means like it's not moving. So therefore D is there. So now we're dealing with B and F. So they're going with a when you look at the angle, it's even though they have a different setup of the diagram, I mean like this force is going that way and that force is going this way. When you carefully look at the angle, it's the same angle. When you look at the resultant force, is also adjacent to that angle. So this cosine meaning like the resultant force is adjacent to the angle. So the amount of work is the same thing again. So we're gonna just put the B and F. Yeah, there's no, one student came and asked me this question even before I do my lecture here, because he is sprinting so fast. So I told him, there's no need to calculate anything here. I like your SAT. Yeah, I don't know why the students are so afraid to take SAT, ACT, but these MCQs are developed by professors from all over the United States, or university and schools. Okay, and they are very valuable assets to the education that these people from the business, want to get rid of that tests. But the standardized tests are so important to train your intelligence and your mind to be able to work it out. And I have no idea why. There's a lot of things going on, to dismantle that system. It's wrong, by the way. But of course, we can't say anything because America is seriously corrupted, and the only thing that they want to worship is money. So anybody who has some money, in which way, however they got it, loads and loads of money by fooling people, by taking money from the people, I don't know. However they got it, they have it, and they want to get rid of everything that their children cannot be able to pass these tests, and that's wrong. It's actually not supporting the education system. It's actually destroying the education system. Just because my kids cannot be able to do it, and I have the money, and she can go to this school or he can go to that school and cannot be able to get this or that degree, we're going to get rid of that exam, is wrong. All right, if you make everything so easy, what you got is only the easy thing. How can you be able to use the easy thing? The only way you can be able to do it is just fake realization of yourself, and you will be using people who know to do the work you want them to do, like buying the slave. Slave is us, of course, who will calculate whatever you want to do for them in their businesses. But anyway, so that's what's going on. Of course, from their side, it's not necessary because they've got the money, right? So they've got the money, so they can. But do it for yourself, but not destroy the entire system where a lot of the student can be able to benefit from. And destroying the book and the system and the knowledge is not now. It's been like age-old thing. Okay, long time ago. Also, so many government or people with money always burn the books, right? Burn the books, but burn the knowledge. So not everybody can be able to get educated and become wise or understand. I don't know. I'm just saying it because that's what's going on today, and it's in my mind right now, like every day. I'm thinking about why it's not right. So anyway, so let's go back to here. No, you don't need to do calculation. This is just by looking at the diagram, you can be able to identify the same direction, force, and motion. It's going to give you work. The amount of work is showing you here is positive, and the amount is positive PD, which is the same thing as here. So therefore, if you get A, this is the same, so you don't even have to calculate anything, just write down A and E. The second one, the same thing. Look at this. B and F also the same thing. So you're down to this too. When you look at it, this one says 0, that one says negative, so that will go to the last one, and then second followed by that. That's it. So how easy it is to of course I have to explain it to you. If I do it by myself, it's really fast. Then we'll get into some point 1-5. So here we're gonna need the situation in the book. Okay, so match that situation with the amount of work. Okay, so let's go to the book site. I think there's something's going on here that I don't know. I can find the problem. This is actually 7.16, so maybe they got the wrong, I think, problem here, which is not in there. This is there, 7.16. So I think somebody write the something wrong. So I can't find this on the textbook. So I believe that they miss it. Or if you found this, let me know. I couldn't. Um, so here it's just asking you to go ahead and match, right? Since we don't have the situation, we're not going to do this and we will skip this, yes? But even though we don't have the situation, we can be able to understand, even though we don't have this true diagram here for us. This is Ford for focus, so therefore see like how heavy, 358 kilojoules. So that's a lot of work that can be done with this guy. Yes, so um, the work that can be done is here. Okay, and of course that's your conversion to kilojoules. So that's the force in the of course the feet. Okay, which is this guy. The second one is a package lighter, 234 pound-feet, and the third one is mosquito is a negative, so very very light, and then of course the last one is your cow here, We can match it by just looking at the weight, yes, of it, so we can be able to get the work. Let's go to 7.1-6, which actually is this guy. It is written here as 7.1-5. Alright, so the next example is you want to lift a block of mass M. So this guy right here from the floor to a height. And you're going to go about D, from there to there. And you will push it up with a constant rate, okay, using a constant force. The problem continues. So you have an opportunity to use a single machine, so frictionless ramp, and that is because you want to reduce the amount of force needed to do that job, like in case A. Or you can simply lift that block up straight up, straight up meaning like go straight 90-degree up, like in case B. Two different ways to get that thing up there. And then the question asks you, so case A and B, which one is going to do less work? So every time you think about work, you have this force, okay, going a distance. So you have to determine the force and you have to determine the distance. So the distance amount is D. The force amount, okay, is F and F. Of course, then you've got to think about your D is already given there, for you, which is D in this case. So that's done. So we have to concentrate on the force and see if the force is the same. So when you look at this force, you're actually lifting this weight up. So therefore, the amount of force that you have to give it, okay, to get this block up, it's its own weight. You're lifting the weight, so that's equal to mg. So here you have already calculated the amount is force and the distance is d. That's your I would say work. They go with u, you can go with w, it's the same thing. So let's figure this out. Here we already got the distance amount is d, so we gotta figure out this, okay, force. So when you look at the force and when you look at this force, we have a force body diagram. So you're gonna do this, okay, like you always do, okay. So since the direction of the force is completely cosine theta, because it's adjacent, the direction of the force is adjacent to the this little triangle that we just draw against that. So therefore you also have the weight is always like this, okay, mg here going down. So you have two different forces going down like that. So in order for you to get this, your F got to be mg, and since mg is going in this direction, so that's opposite of that. So therefore sine theta. So your f is mg sine theta because of this incline. Okay, it's not flat horizontal like this. Yeah, so you're not pushing this way, you're pushing that way. So that theta is your this incline angle, which is the same as that. Yeah, so therefore we account for only this guy, and that's where you get the mg sine theta. Yeah, for that. Of course, and then you're gonna go the distance that way, and we're gonna use it. The distance is going L direction. Yeah. So in order for us to be able to get the L against D, you're gonna have a sine or theta is equal to opposite. Okay, by hypotenuse like that. So from here you get D is you do your algebra, okay, and I would just write it L, yeah, and sine theta. So L is D by sine theta. Yes, and I'm gonna write it here. L is equal to D by sine theta. And we're gonna put that, okay, into the work. So right now we know the force. So work for that is F, and then time, the distance L along this horizontal slope, okay, because it's going on this direction, because your object is on that slope. So this, I'm gonna just use it as a horizontal alignment to ground, okay, for this guy. And then your force is sliding that way, moving this thing up the slope, yeah? So therefore, that's your force, and that's the distance it took, is L. And now you're going to put the force times your L is equal to D divided by sine theta, yeah? And this sine theta, because your F is, again, mg, yeah? mg sine theta. And then times d by sine theta, d by sine theta. So this sine theta is going to cancel. Yeah? So you're going to get u is equal to mg, and then d. It's the same thing as this. Yeah? So therefore both cases require the same amount. So anyway, so that's how we calculate. Okay? And here's a better systematic way of writing, yes, instead of me working in my brain, but it's the same thing, yeah. So see, both cases require the same amount. So here is your F here, and your D here. We start to calculate. Your X direction is 0. Your F direction that's going this way is mg sine theta, yeah. Then it's about the same thing, yeah. They also call this L. It's just a way of writing it. So your force is mg, and then sine theta, and then your L, we put it in, and your L is d by sine theta. Yeah? So therefore, sine theta is cancelled, and you're going to end up with mg d. So this is here, yeah, and your angle is right there like that. The rest of them are the same thing. You do like this, y, and then your x. This one also the same thing. Yeah, y. I think this is kind of block this. I should go back. Yeah, block this one, but it's the same thing because you're nothing but slope is there. Yeah. So anyway, for you, probably you might wanna, if you want to try it. You know, if you don't want to try it, that's okay too. You first draw the coordinate lines, and then put in the diagram into it, and you can be able to see this f is mg sine theta. Okay, after doing your trigonometry, of course, and your geometry, and again this d divided by L is sine theta. That's where we get d divided by, okay, L is sine theta. Therefore, L is d divided by sine theta. Okay, that's your algebra. And that's where we plug it in here, d by sine theta. So sine theta is cancelled with this mg sine theta for f. And you will end up getting mgd. Okay? Alright, the next problem is on the pulley. So you have a block of mass, this guy, and you want to lift a vertical distance, this guy, d. You're going to use a constant force. Instead of a ram, you now have the opportunity to use a system of pulleys to do this job. Of course, we want to compare the work again. When you look at it, we already identified d as the same. So we're going to figure out our f. So you do the same thing. You're gonna break it down into x, yes, y and x-axis, just like that. So that's, you should do it in your head like this, okay? In my head, the first thing I do is that, and then of course your fy is completely zero because your force going down and your motion going up like that, so therefore it's zero. So now we're down to x component. So the only weight that we have is your mass, which is mass times gravity, and we are lifting that weight up. We have one pulley system and two pulley system. So for two pulley system, your force is lifting only half each, here half and here half, so mg divided by 2. In your full pulley system, you are lifting the whole thing with one single, this is completely full, so therefore you're only single pulley and lifting the whole full weight of mg. So when you put that into work, and work is, as you know, force and distance. We are gonna put that in, force and distance. So if you put the force and the distance, you will get, for single pulley, mgd. For double pulley, you're gonna put, because you go up 1 and 2 times, so the distance. So you have force times 2d, okay, going up this way and that way at the same time. And of course, you want to put your f is mg divided by 2, and then times 2d. So this 2 is going to cancel out, so you're going to be getting only mgd. So this one is correct. Both cases require the same amount of work because you end up getting mgd anyway, because this is a single pulley system and this is a double pulley system, lifting double distance at the same time with half load on each pulley. will give you the same amount of work. Okay, now we're going to write it systematically. See, Fy0, you're going to use a half of the weight on each pulley, mg2. So you have a distant d for this pulley and distant d for that pulley. So put that in. 2 will cancel out. You're going to be working only mgd. This is a single pulley, so it's the same thing. You know, your F going down is what you pull up. So therefore Fmg. U is equal to Fd. Okay, so therefore you get mgd for magnitude. You know, work doesn't have direction. So even though it's going on the Fy axis, yes, it's the same thing. Of course, if the I would say the force diagram actually that they draw is in the textbook. Okay, it's probably like this. Okay, but it's the same thing anyway. Doesn't matter y or x. You can switch it in any way you want to. Like I say, like in some of the texts where they would test you, the symbol really doesn't matter. You can switch these x's in many different ways. As long as you're calculating that force, you can give like whichever x or whatever symbol you want to do it. Okay. So don't always think like y always got to be the vertical one here. You can switch it like this too. Then we will get into kinetic energy. A lot of the book abbreviate KE for kinetic energy. Some make like a different symbol, to confuse you. You can write whatever you want to write. Energy, it just you have something to do work. If you don't have that capacity, it's impossible to do the work. And work is just some force making something going a distance. And of course your capacity is to generate the force, and we call that the energy. Then we're going to think about a block, and the block is being pushed along a smooth surface here. Smooth meaning like we're not going to think about friction on that line here, force line. We're going to draw a free body diagram. Here's your y and x. Your y has a weight and your normal force perpendicular to that weight. And we have our force in the x direction. Your applied force is P pushes that block, and it's going to cause that block to move in the x direction. So that force definitely do some work on that block, because it took the direction, it took the distance, So what is the work done by the force if the block travels through a distance? So now the problem give you the distance is delta x. So we put that into work. So the work done is, with this force, this amount of distance has been made. So we write that down. And now that work done by the force on the block, and we're going to convert that to something. Okay, so here what it meant is like physically what you see, okay, is just the block move, and it moves, right, physically move from this point to the distance it took, from the force. And the whole thing is called, you've got some energy to do that move. So, and we would just write it like, oh, it got the work is converted to energy of motion, and we call that kinetic energy. Okay, because without that energy transfer from the force to the particle or the body that you are studying, in this case this guy, it won't move, okay, from that position to the next position. It will only move the amount of energy you will get from that force. Okay, so right now you can do two things if you get like a extra energy to your system. One is you store it, or the other one is use it to take a distance out of it. Okay. If you store it, we call it PE. And you can only store it if you have enough space in your system. You can't store it if you don't have enough space in your system as a potential energy. Okay. And when you don't want to store and you have just, like you don't have extra space to store, then you will have to use it to move. Okay. And that's what exactly happened to it. Yeah. It can be stored energy, and it has a sufficient energy to keep this at this position. Now you got extra energy. That extra energy cannot be stored in this body to keep that position at that location. Okay, so therefore we're going to use that energy and do the work to take that distance delta x, all right, to move the new position, and work happened. And in order for that work to be done, you have used that amount of energy, which is kinetic energy, usually calculated as the amount is 1/2 mv squared. Yeah. The velocity that it used to move this mass, and this is just adjustment calculation coefficient to balance, the rest of the environmental factors of this planet, which is our Earth. Okay. Of course, there are many different coefficients, by the way, but this is the I would say like the nearest one that we can be comfortably use for many different systems. Okay. All right, then the next one is we're going to use your Newton's second law, and that is your equation of motion. And you will determine the acceleration of that block. So we will use F is equal to ma. Don't worry about that. That's just showing you that we're thinking about all forces on that block by breaking the resultant force into x and y components. And of course, since we're going in x direction, so we just put the little x right there. And all the forces in that direction is going to give you mass time your acceleration. Okay. Calculate. We're going to put it in. Your p is m. Acceleration on x-axis. We're going to take acceleration out of that equation. So put this to that side. So you will get p divided by m. That's your algebra. And acceleration amount is that much. Okay. It comes from here. This goes to that situation where we use a symbol P for F. Okay. And you do have a y and x, but we concentrate this because the motion is going that way. Okay. Since the motion is going that way, we only have an x direction. Since the motion goes that way, the aspect of the motion will go that way as well. Your velocity and the acceleration. All right, I don't know what is this. Something seems to be blocked. So let's go and see 7.2-1 over. Okay, so this is 7.2-1. So we did that. We are supposed to be on here. So using the kinematics relationship. So it's just taking the acceleration against the direction, x-axis direction, and then velocity against the, of course, differentiation of a little b. And that, I think, you don't have to do it because it goes into your calculus area. And so all they want you to do is determine the work done by force P on the block, and we'll have to write it in the integrated expression. This is not included. I'm just going to talk it to you so you can be able to at least get the idea of it. You don't have to calculate this. Okay. So of course we put that P into here and take our constant mass as constant. So there is no need to integrate. So we will just integrate the velocity, and velocity is again breaking down into velocity 1 and 2 because you are pushing it. And we do have acceleration, which is this guy. So as soon as you have acceleration, you do have a velocity variation. So that's where you have 1 and 2. It's just showing you that I have a variation of velocity, which is leading to creating this acceleration on my mass. Yeah. So that's what is set, and of course I divided by 2. And this is just trying to represent the force, okay, in the calculus way. So you can be able to see, yeah, the potential, I would say like kinetic energy, okay, equation right here. So if you look at it, this guy, see this, yeah, and if you rewrite it, this 1 by 2, and this is just showing you the resultant velocity. This is simplified version, which is not breaking down into velocity 1 and 2. It just is showing you the net velocity is equal to actually, yeah, integration of your force in terms of x, and the whole thing is your kinetic energy. It's just showing you, how your force is pretty much your energy to cause the kinetics, which is your motion, okay, and we put it into mathematical formula. Yeah? Your force taking a distance is making that amount of work, and that amount of work can be, okay, represented in another way, which is in terms of energy, yeah, which is this guy, 1 by 2 mv squared. We're going to come back to this method, okay, slide right here. I think there's something is blocking there. So anyway, I just explained that to you, yes. So this is where we can be able to see how acceleration p divided by m is connected to, see, the kinetic energy at the end. I just show that to you here, yes. Yes. So when we solve this equation, half is going to come out, your mass, and the whole thing, we can write it this way, okay? Of course, here we're still in a component of velocity, because to account for the acceleration, and in order for acceleration to happen, you need delta, change in velocity. This means change, and that's velocity. Change in velocity. Every change has a final velocity and initial velocity, okay? And that's what you're seeing here, okay? And you go back to your Eureka video, and these are very old video, but you can find this a cartoon video, Eureka, and you can be able to see the kinetic energy. Look for it manually. Then we will get into kinetic energy. Here in this book, they go by T. A lot of the book, they write this way. A lot of the professor, they write that way. It's up to you, If you don't like T, just use KE. If you don't like KE, make your own symbol that goes with your head. Alright, so the energy possessed by a body due to its motion is going to be kinetic energy. And that can be calculated by 1 by 2 mv squared, And you were asked, like, sometimes you can feel like your work is, work and energy is pretty much related, very closely related, by the way. But they're not equal, by the way, okay? They're just closely related, and we use a back and forth work and energy as if they're the same. But just be very careful, they have a very distinct formula. Even though they come very close to each other, they're different, still different, and the units are the same, just because of the unit is the same. Student, like, this is another time that I want to tell you, or what you think is not what it is, okay, in some situation. So therefore, don't judge other people, because the way that you think about that person is just your own mind. It isn't that person, You can't just go and say like horrible things against a person backed by people who will support what you say, would be very mean to the person. That's why God told us not to judge anybody. Is including yourself, by the way. You're not supposed to judge yourself either, even though we say like, oh, judge yourself first, analyze yourself first. But in fact, we don't judge anybody, including yourself, okay, if we go with the spiritual way. Because we do not know, okay? The point is we don't know. And even our system, our own body can betray us in many different, times. Telling the truth, you don't own your own body either, because it is living. Because there's so many different, living things living in your system, in your body, from viruses, bacteria to the organs also have their own, way of living. Okay, many different gazillion of life inside of your body, by the way. So it will go with its own system life instead of your nervous system life that okay, with your mind. It's a two different thing. You do not own the physical part of your body, by the way. You thought like you do, okay, because you have some control with the mind that can sometimes control your body, because you're maintaining it because you want to live, okay. Actually, your physical body want to live, okay, because the physical body actually own your mind, not the mind owning your body, by the way, okay. So anyway, so just make sure that the units are about the same, but they have a totally different meaning, and they're very closely related, almost to the point that they're the same, but they're not, okay. But for level 1, you can just take it like they're the same. It doesn't really hurt much. It just in which way they're not the same is the meaning, or in terms of the physical phenomenon, they're not the same. Work is more of a physical thing, and energy is more of a measurement thing, okay. All right, let's go back to the energy balance. And this is another situation where we are supporting that work and energy are related, but they're not the same, because we have the work and energy balance. So if you do the work on a particle, they add the energy to the system, and some of the energy you use on work, and some of them you store it, okay. Like I say, if your system have extra space to store the energy you just gain, you can store it, and you're going to use some percentage of it, okay. So this is where we try to teach the student that the work in kinetic energy, potential energies are back and back, like they go always in dual like that, okay. So sometimes you use a percentage of that, and then sometimes you store it in your system. So there is a balance between work and kinetic energy. Sometimes they balance on. Sometimes one override the other, or one go over the other. Depends on how your particle or rigid body is in relation to the environment. So the initial kinetic energy plus the work done by all forces equals the final kinetic energy. So here, this is your work kinetic energy balance. Your work is U, your kinetic energy is T. And then you can add them up, and you can be able to get second kinetic energy, or the sum of the kinetic energy. Then we will go into conceptual example 7.3-1. So you have a 2-air hockey, okay. Here is your 2-air hockey, your goal line right there. And then you have mass 1 and then mass 2, which is 4 times of mass 1, at point A and B, okay, and with the force, this F, right, subjected to A and B. So hockey pucks, they're resting on the table on the air, with the air on, okay, and then the 2 pucks are pushed across the table with a constant and equal force. It is an equal force because we are using the same symbol. You don't even need the amount of force. It just the symbol is saying that you're using the equal force, because F is equal to F anyway. then you're gonna to neglect the friction. So it's one work, reduced in calculation. We're gonna assume there's no friction, which, so the question is, which park will have the greater kinetic energy upon reaching that goal line? So if you push with the same force, they will move. Yeah. Now this is heavier than that. Yes. So you got to think about the kinetic energy. So kinetic energy we already calculated. This book go by T. So I'm just going to write a dual symbol right there for you. Because some students don't remember T and U and all that. And then of course we bring our kinetic energy, equation. So kinetic energy is definitely concentrating on the mass and its velocity. Yeah. And your mass is different. One is m and the other one is 4m. So therefore, if you take 4 out of it, it will go this way. Divided by 2, so 2 and then 2. So the second one is going to get a 2, right? I would say like, or you can also leave it as it is to compare with the other one, and just take 4 out of it. 4 out of it, because if you put m, this is m. If you put 4, you're gonna get 4 times of that thing, the whole thing. And that is what student would calculate every time they have to do the kinetic energy. Okay, because it asks you particularly for the kinetic energy. But the thing is, like, you have to go back to what we just learned. Kinetic energy is equal to kinetic energy plus initial kinetic energy plus work. Okay, work done. So that is the major thing that a lot of the students forget to apply. They always go straight to the final kinetic energy, forgetting about this thing. So make sure that every time we think about the kinetic energy, it is related to the work done with some kinetic energy. Okay, so if this initial kinetic energy is 0, then you would have the same kinetic energy, and the work amount is going to be the same because this is 0 out. So you have to identify what is the initial kinetic energy for this situation. So the initial kinetic energy is defined right here. It said it is resting. So therefore that is 0. So therefore your final kinetic energy entirely depends on the work. Okay, so when you look at the work, they are at the same distance, from the finish line, and they are using the same amount of force. So therefore your work, again, we go back, force, time the distance d. So doesn't matter how different their masses are, you would have the same amount of kinetic energy finishing that goal line, because the initial kinetic energy was 0. Okay, so that's how we answer. So let's take a look at your answer. So if you go back to that problem here, that would be 3, I think. I try to close that thing and can't be able to do it. So we're at 7.3, I think. This guy, So yes, so this is correct. So UT is the same as your FD, because we don't have. See that how they write it? That doesn't really explain. So that's why you have to listen to my lecture. So you're gonna have a understanding of how we get rid of this initial kinetic energy, and getting that one 0. So this and this is going to lead to that. Okay. Yes. All right. And then the next one is, which puck will reach the goal line first. This one is pretty easy. This is asking you speed. Speed, because it said which puck will reach the goal line first. The other one is asking you the work that you have to do to get to there. Very different. Work is the same, but speed isn't, because of the mass. Because your speed completely depends on the mass. Okay. So we go back to the very first equation like that. So we're now being asked that since we have this the same, all you have to do is put this to that side and put also to that side, and of course you're gonna get like this. Yes. Okay, move that over there, move this down there, so you're gonna get that, and then you can square root it. And you will get this. Your T is your work done. So I'm just gonna write it here. There's no space to write, so let me write it on this side. So what you're gonna get is 2T, it become your work. Divided by, and that's your V. And then this U is FD, yes, because it's the same thing. So you're gonna get like that, of course. But your M is different. So the first M is going to be like this. So FD, that's the first M, and second M is 4 times of M. So when you look at it, this is your speed for M1, and this is a speed for this body. Okay. So if you calculate that, yes, since these are the same, you only have like 1/4, yes, square root of 1/4 against 1 around square root of 1. See like how we calculate that. Then we come to axle to calculate. This is see, square root of 1. So if you look at the square root of 1, I just want to show you this formula. So square root of 1 is 1. Square root of 1/4 is 0.5. So this is faster. Okay, so let's go there. And puck A is faster. It will get to the goal line first, even though they do the same amount of work. Okay, so that's a differentiation between the motion velocity and the energy and kinetic energy and the work done. Okay, how they are relating to each other, and you have to be able to understand that 3 situation very, very clearly. Okay, so again, that comes from experience, years of studying and years of doing an incredible amount of problem, by the way. Right now, you may see it, but you might not get it perfectly. It will take some time for you to get it. You might get one single problem, but when you encounter another one or more complex problem, you will forget about it. So don't forget about it. Work done. Kinetic energy also linked to velocity. Speed is speed. Work is work. Kinetic energy is kinetic energy. So the catch points are total, or the final kinetic energy is based on the work done and initial kinetic energy, and you always have to understand what's the initial kinetic energy. Of course, we're running the lab, and we're not going into components or breaking down initial and the final velocity. But of course, if you, because of the complexity of the track, you will have to come up with different segments and calculate different kinetic energy and the work. But I don't want to torture you, so I said just go with a simplified version of it, and some don't want to do it, and some still afraid of the complexity of the words. It's up to you. If you want to go segment to segment, go ahead and do it, if you have time. If you don't have time, you can just go with the estimate, or estimated version, which is going with the height of it, and that's okay for now. Okay, then we come into the conceptual example 7.3-2. So we have a truck, and that truck is driving along a horizontal road with a constant velocity. Of course, it has this motion and is retarded and eventually halted by a set of crash barrels. So here are your barrels right there, and halted meaning go to stop. And then the amount of barrels and sand within the barrels are arranged in such a way to decelerate the truck at a constant rate. And then we do 4 test runs performed, where the velocity and mass of the truck are varied. Okay, so in each of the following situations, the barrels stop the truck in the same distance. So we have 1,500 kilogram mass in situation B. Of course, in A, 10 meter per second, you have 15 meter per second. Speed is going up. With a smaller load, your truck is 1,000 kilogram. Here, 1,000 kilogram with 10 meter per second, and 2,000 kilogram with a very slow 5 meter per second situation. So we have to rank the force required to stop the truck, and we have 4 different situations, and we gotta rank it from greatest to the least. Okay, so this time we need the force required to stop. Yes, so therefore we're gonna start writing our work energy balance equation, initial and then the final, because our initial are already given there for you. So we've got to come up with the force. So therefore we're gonna get the force out of it. So force is related to U, so that's the FD, yes, and T is 1/2 mv 1 square. Okay, of course it skips about 2 steps right in here. That's all right. This, we're talking about the initial velocity, so therefore it's this guy, and that is this, but it has a negative force because you are the force required to stop. So these are the things the textbook is not showing you, the steps that they skip. So therefore when you take plus u to the other side, you got minus u, and that minus and this minus, they cancel, so you get FD here. And you don't have the velocity is at the end it becomes 0 because your question said that it halt, right? It stopped, so therefore 0 velocity right there. So we will calculate F here, and we will take this D to the other side. So 1/2 m v1 squared divided by D, and then we are going to put in your mass, your velocity, initial velocity, indicated by little 1 right here, and then of course the distance is going to be D. Since distance is not given to you in the problem, we're just going to use D. So the answer will come out in terms of D. So put the mass in here, put the velocity in here, and calculate. So we get 75, 112.5, 50, and 25. And then we're going to rank it. So that's the highest, followed by this, and followed by that, and that's the least. Okay. Then we're going to get into the next section. So here we will take a look at the conservative force. So a conservative force is nothing but a force, and it's going to conserve. Conserve means store, the mechanical energy. Mechanical, just we're dealing with the motion. Okay. Mechanical engineering technology is all the technology that we use to create the motion, or to stop the motion, or to store, again, the mechanical energy. So this means that the work done by a conservative force is completely reversible. Okay, and maybe retrieved or recovered at a later time. So every time you do the work, and if you did that work with a force, but that force is conservative, you can take that force back into the system, okay? And you can use it whenever you want to use it, and you can store it when you want to store it, and we call that the conservative force. Not every force is conservative, okay? Only certain forces are conservative. So let's take a look at it. Since we learned what is a conservative force, we also have to learn what is not a conservative force. So a force, that does the work, that puts into or takes energy away from the body. The energy is not stored, it cannot be recovered. So there are forces that you just use it up. You use it to do the work, and you can put it back into the system. You cannot store it again. You cannot recover the force. It would just use the work or dissipate as heat, to the environment, or you're going to lose it to the environment because the environment factors are going to take the extra force that you didn't use in the work, okay, out of that situation. So you can't recover. So those type of force, we call that non-conservative force. Then we're going to compare conservative and non-conservative. So here is your work done by conservative forces. Okay, so that type of work does not depend on the path, right, taken by the object to get from the initial point to the final point. So here again, if you think about the conservative forces, the work done by those type of force, because you need a force for something, a system to do the work, of course, work here is you. It doesn't depend on that path, so that force does not depend on the path taken by the object to get from the initial point to the final. When you think about the non-conservative force, it depends on that path. Non-conservative forces. So you move this object to another position. So your work has been done here, and if you're using a non-conservative force, it depends on that path, that the object is traveling on. So here, when you look at this diagram, okay, and here's the path, look at that, so here is your object going from here, actually the initial is here, so going from here all the way to here, so this is a path. Conservative, they don't depend on that path. You can go this way, or that way. Non-conservative depends on which path you're on, okay? Then we're going to get into 7.4-1. I'm going to stop the second video here, and we will continue to the third one. Try to make it 1 hour here for you guys.